In the spring of 1943, a German intelligence officer stationed in Stockholm reviewed a peculiar report that had crossed his desk from neutral Sweden. The document described an unusual construction project underway at a Canadian research facility near Toronto, a massive concrete structure that Swedish engineers who had visited the site could not quite understand. The Germans, who had invested enormous resources into jet propulsion research and considered themselves the undisputed leaders in high-speed aerodynamics, dismissed the report with barely concealed contempt. A notation scrawled in the margin of the file captured the prevailing attitude perfectly. The Canadians, lacking both the industrial sophistication and the scientific expertise of the Reich, were likely building nothing more than an oversized warehouse, or perhaps a misguided attempt to copy British wind tunnel designs without understanding the underlying principles. The intelligence was filed away as insignificant. 1. More example of Allied nations engaging in wasteful projects that would contribute nothing to the technological arms race that Germany was confident it was winning. That dismissal would prove to be one of the more consequential underestimations of the war, as the structure taking shape in the Canadian countryside was neither a warehouse nor a copy of existing designs, but rather an accidental revolution in aeronautical testing that would shape the future of aviation for decades to come. The story begins not with grand strategic planning or visionary leadership, but with frustration and improvisation, two qualities that characterized much of the Canadian war effort. Dr. John Mackenzie, a Scottish-born aeronautical engineer who had immigrated to Canada in the 1932nd, had been tasked with solving a problem that was becoming increasingly urgent as the war progressed and aircraft designs pushed toward higher speeds and altitudes. The existing wind tunnels used to test aircraft models and components were designed for the relatively modest speeds of propeller-driven planes, typically operating at velocities well below 300 miles per hour. But intelligence reports filtering back from Europe suggested that both the Germans and the British were experimenting with jet propulsion systems that would enable aircraft to fly at speeds approaching and potentially exceeding 500 miles per hour. At these velocities, the aerodynamic behavior of aircraft changed dramatically as air compression effects became significant, and the principles that governed low-speed flight no longer applied in straightforward ways. Testing aircraft components for these high-speed conditions required wind tunnels capable of generating airflows that approached the speed of sound, a technical challenge that no existing facility could meet. The British had made some progress in developing high-speed test facilities, but their designs were based on incremental improvements to existing technology and were proving inadequate for the velocities that next-generation aircraft would achieve. The Americans, with their vast industrial resources, were also working on the problem, but were encountering unexpected difficulties as they discovered that simply scaling up existing designs did not produce the results they needed. Mackenzie had been studying the problem for months, reviewing the literature on high-speed aerodynamics, and corresponding with colleagues in Britain and the United States who were grappling with similar challenges. The conventional approach to building a high-speed wind tunnel involved using enormous fans or compressors to force air through a carefully shaped test section where models could be mounted and instrumented. But as the desired test speeds increased, this approach encountered fundamental limitations. The power requirements grew exponentially. The structural stresses on the tunnel components became severe, and the airflow itself developed instabilities and turbulence that made accurate measurements nearly impossible. Several research teams had concluded that building a wind tunnel capable of reliably testing components at near-sonic speeds might simply be impossible with existing technology, that the engineering challenges were too great and the costs too high to justify even attempting such a project. Mackenzie, working in a modest office at the National Research Council facility outside Toronto, refused to accept this conclusion. His refusal was born partly from scientific curiosity, partly from a stubborn determination to prove that Canadian engineers could solve problems that had stumped their better-funded colleagues elsewhere, and partly from a practical recognition that if Allied aircraft were going to compete with German jets in the skies over Europe, someone needed to figure out how to test them properly. The breakthrough, when it came, emerged not from careful theoretical analysis but from a mistake in the initial design calculations. Mackenzie had been sketching out a novel approach to the wind tunnel problem, one that inverted the traditional logic by keeping the air relatively still and instead accelerating the test models through it at high speed. This concept, while elegant in theory, presented its own set of daunting engineering challenges related to model mounting, instrumentation, and the enormous forces involved in rapidly accelerating and decelerating test articles. As he worked through the mathematics of this reversed approach, trying to calculate the power requirements and structural loads, he made an error in his equations that led him to vastly underestimate the size of the facility that would be needed. Based on his flawed calculations, he prepared a proposal for a test facility that seemed almost reasonable in scale and cost, certainly ambitious, but potentially achievable with the resources that might be allocated for a priority war project. He submitted this proposal to his superiors at the National Research Council, along with a request for funding and authorization to begin preliminary design work. To his surprise, the proposal was approved with unusual speed, pushed through by administrators who recognized the strategic importance of high-speed aerodynamic testing and who were eager to demonstrate that Canadian scientific institutions could contribute meaningfully to the Allied technological effort. It was only after construction had begun, after thousands of tons of concrete had been poured and enormous steel structural members had been fabricated and installed, that Mackenzie discovered his mathematical error. The facility being built was far larger than his corrected calculations suggested was necessary, oversized to the point of seeming absurdity. A properly designed facility based on his original concept would have been perhaps one-third the size of what was actually taking shape on the construction site. Mackenzie spent several sleepless nights contemplating this discovery, torn between the obligation to report the error and the fear that doing so would result in the project being cancelled and his career being destroyed. But as he reworked his calculations and tried to understand what the consequences of the oversized design might be, he began to realize that his mistake might have accidentally solved a completely different problem, one that he had not even been trying to address. The enormous size of the test section, combined with specific geometric ratios that had emerged from his flawed mathematics, created conditions that would allow air to flow through the facility at extremely high speeds, without developing the turbulence and instabilities that plagued smaller designs. In essence, the accidental oversizing had stumbled upon a scaling relationship that made high-speed testing practical in ways that conventional designs could not achieve. What had seemed like a career-ending blunder was actually a serendipitous discovery that would make the Canadian facility the most advanced aerodynamic testing installation in the world. The construction of what would eventually be designated the Canadian High-Speed Aerodynamic Research Facility proceeded through 1943 and into early 1944, encountering the typical delays and complications that afflicted wartime projects competing for scarce resources and skilled labor. The sheer scale of the structure drew attention from military and civilian observers who struggled to understand what purpose such a massive installation could serve. The main test section was a concrete chamber, more than 200 feet long and 40 feet in diameter, dwarfing any existing wind tunnel in the Allied nations. Massive steel doors at each end could be sealed to create an airtight envelope, while an array of powerful compressors and vacuum pumps, salvaged from various industrial facilities and repurposed for this application, were installed to control the air pressure within the chamber. The instrumentation systems were equally ambitious, employing the latest electronic sensors and recording equipment to capture data during the brief moments when test conditions could be maintained. To outside observers, including the German intelligence services that received sporadic reports about the construction, the facility seemed like a grandiose waste of resources, a typical example of inefficient Allied duplication of effort and failure to coordinate research programs. German aeronautical engineers, reviewing the fragmentary intelligence about the Canadian project, concluded that the Canadians were attempting to build a conventional wind tunnel but had bungled the design through inexperience and poor understanding of the underlying physics. This assessment reinforced the Nazi conviction that Germanic technical superiority would ultimately prevail over the numerically superior but technologically inferior Allied nations. Mackenzie, meanwhile, was working frantically to understand and optimize the accidental design he had created. As construction progressed, and he could take measurements of the actual structure, he developed increasingly sophisticated mathematical models of how air would behave when forced through the enormous test section at high velocities. His calculations suggested something remarkable. Under the right conditions, the facility would be capable of generating steady airflows at speeds approaching and potentially exceeding the speed of sound, velocities that no other wind tunnel in the world could achieve. Moreover, the large size of the test section meant that relatively large models could be tested, providing more accurate data than the tiny models that had to be used in smaller facilities. The accidental discovery had created a facility that was not just incrementally better than existing wind tunnels but represented a qualitative leap forward in testing capability. Yet Mackenzie was also aware of significant risks. The enormous forces involved in moving air at near-sonic speeds through such a large volume created structural loads that approached the limits of what the concrete and steel construction could withstand. There was a real possibility that operating the facility at its maximum design speed would result in catastrophic structural failure, potentially killing everyone in the building and destroying years of work in an instant. The mathematical models could predict the general behavior of the system, but there were too many unknowns and too many simplifying assumptions to be completely confident that the structure would hold together when subjected to the extreme conditions of actual operation. The first low-speed tests of the facility were conducted in March 1944, with the research team gradually increasing the airflow velocity while carefully monitoring structural stresses and looking for any signs of instability or unexpected behavior. These initial tests revealed numerous problems that needed to be addressed, from leaks in the seals around the test section doors to vibrations in the compressor systems that threatened to tear the equipment apart. Each problem was methodically diagnosed and corrected, often through improvised solutions that drew on the practical experience of the technicians and engineers rather than textbook procedures. The team developed a culture of careful experimentation and incremental progress, never pushing the facility beyond what they were confident it could handle, always maintaining margins of safety that reflected their awareness that they were operating in unknown territory. This cautious approach frustrated some of the military liaison officers who wanted immediate results and questioned whether the enormous investment in the facility would ever produce useful output. There were suggestions that the project should be canceled and the resources redirected to more conventional research programs that had a proven track record. Mackenzie and his team found themselves fighting a two-front war, one against the technical challenges of making the facility work as intended, and another against skeptical administrators who doubted whether the Canadian effort would produce anything of value before the war ended. The breakthrough came in July 1944, when the team achieved stable airflow at velocities exceeding 450 miles per hour, speeds that no other wind tunnel had reliably attained. The test section remained stable, the instrumentation functioned properly, and for the first time, researchers were able to gather detailed data about how aircraft components behaved at the edge of the transonic regime, where conventional aerodynamics began to break down. The data revealed phenomena that had been predicted by theory but never directly observed, including the formation of shock waves and the dramatic changes in lift and drag that occurred as airflow over wing surfaces approached sonic velocity. More importantly, the tests demonstrated that the facility could operate repeatedly at these high speeds without suffering structural damage, validating Mackenzie's calculations and proving that the accidental design had indeed solved problems that had stumped more conventional approaches. Word of the Canadian success spread quickly through the Allied scientific community, reaching researchers in Britain and the United States who had been struggling with their own high-speed testing programs. The initial reaction was skepticism, with some experts suggesting that the Canadian results must be flawed or misinterpreted. How could a relatively small team working in a facility that had been designed by accident achieve results that well-funded programs at major research institutions had failed to produce? The skepticism gave way to astonishment as visiting experts inspected the Canadian facility and reviewed the data, confirming that the results were genuine and represented a genuine advance in aerodynamic testing capability. The strategic implications of the Canadian achievement became apparent as the war in Europe entered its final phase, and intelligence about German jet aircraft became increasingly detailed and alarming. The Messerschmitt 262 jet fighter was appearing in growing numbers over Germany, demonstrating performance that far exceeded anything the Allies could field. British and American engineers were racing to develop their own jet aircraft, but they were hampered by limited understanding of the aerodynamic challenges involved in high-speed flight. The Canadian facility, now operational and producing high-quality data, suddenly became a critical resource in the Allied effort to close the jet technology gap. British aircraft manufacturers began sending components and model designs to Toronto for testing, seeking data that could not be obtained anywhere else. American researchers, who had been condescending toward Canadian scientific capabilities at the start of the war, found themselves requesting access to the facility and trying to understand how Mackenzie's team had achieved what their own programs had not. The tables had turned, and the underestimated Canadian project was now driving advances that would shape post-war aviation. German intelligence, receiving reports about the sudden interest in the Canadian facility and the flow of Allied researchers to Toronto, belatedly recognized that something significant had occurred. But by this point in the war, German capacity to respond to Allied technological developments was severely constrained, and the information was largely irrelevant to the outcome of a conflict that was already clearly lost. The autumn of 1944 marked the period when the Canadian facility transitioned from experimental curiosity to operational necessity, as Allied aircraft manufacturers faced the daunting challenge of designing planes that could match or exceed the performance of German jets. The Gloucester Meteor, Britain's first operational jet fighter, was encountering unexpected handling problems at high speeds, with pilots reporting severe control difficulties and several near-fatal accidents during test flights. British aeronautical engineers suspected that the issues were related to transonic effects, the complex aerodynamic phenomena that occurred as portions of the airflow over the aircraft approached the speed of sound. But without adequate testing facilities, they were designing blind, unable to predict how modifications to the aircraft's shape would affect its high-speed behavior. Components were being tested in the Canadian facility on an urgent priority basis, with data transmitted back to Britain within days of tests being completed. The information revealed that the Meteor's wing design was generating shock waves at high speed that disrupted airflow over the control surfaces, rendering the aircraft dangerously unstable. Armed with this data, British engineers were able to redesign the wing, profile and modify the control systems, transformations that turned the Meteor from a promising but problematic design into an effective combat aircraft that could engage German jets on relatively equal terms. The American jet program, centered around the Bell P-59 era Comet and the more advanced Lockheed P-80 Shooting Star, was encountering similar challenges and benefiting equally from access to the Canadian testing capability. American engineers, accustomed to having the best facilities and resources in the world, found themselves dependent on data from a facility they had barely known existed a year earlier. The experience was humbling and educational, forcing a reassessment of assumptions about where innovation originated and who possessed the technical expertise to solve cutting-edge problems. The Canadian team, for their part, found themselves working around the clock to meet the demand for testing time, with a backlog of components and models from various Allied programs, waiting to be evaluated. Mackenzie implemented a systematic prioritization process, focusing first on tests that addressed immediate safety concerns with operational aircraft, then on data needed for designs that were close to production, and finally on more speculative research aimed at understanding fundamental aerodynamic principles. This pragmatic approach ensured that the facility's unique capabilities were directed toward problems that would have the most immediate impact on the war effort and the most significant influence on post-war aviation development. The technical challenges of operating the facility at its performance limits required constant vigilance and innovation. The enormous power requirements meant that tests could only be conducted for brief periods, typically no more than a few minutes at maximum speed, before the compressor systems needed to cool down and the electrical systems needed to recover from the strain. Each test run had to be carefully planned and executed, with every sensor calibrated and every data recording system verified before the precious seconds of high-speed airflow were initiated. The team developed protocols that maximized the information extracted from each run, using multiple sensors simultaneously and recording data at rates that pushed the limits of available technology. The photographic systems were particularly challenging, as capturing useful images of airflow phenomena at transonic speeds required lighting systems and camera shutters that could freeze motion occurring in milliseconds. Specialized strobe lights were developed, capable of producing intense flashes of light with durations measured in microseconds, illuminating shock waves and flow separation that were invisible to the naked eye. These images, when combined with pressure measurements and force data from instrumented models, provided a comprehensive picture of how aircraft components behaved under conditions that had previously been inaccessible to direct observation. The breakthrough moment that definitively established the facility's importance came in December 1944, when a series of tests on swept-wing designs revealed aerodynamic properties that would revolutionize aircraft design for the jet age. German aeronautical researchers had discovered that sweeping an aircraft's wings backward at an angle, rather than mounting them perpendicular to the fuselage, dramatically reduced the drag and delayed the onset of problematic transonic effects. This discovery, based on theoretical work conducted at German research institutions, had been incorporated into late-war German aircraft designs and had been discovered by Allied intelligence teams examining captured documents. But the theory was incomplete, and the optimal sweep angle and wing geometry for different flight regimes remained poorly understood. The Canadian facility, with its ability to test models at genuine transonic speeds, provided the empirical data needed to transform theoretical understanding into practical design guidance. Tests conducted over a period of weeks, systematically varying sweep angles and wing profiles, generated a dataset that revealed the complex relationships between geometry and performance at high speeds. The data showed that swept wings not only reduced drag, but also fundamentally changed how aircraft handled at transonic speeds, offering the possibility of designing planes that could safely exceed the speed of sound without the catastrophic control problems that plagued straight-wing designs. The implications of this data extended far beyond the immediate military applications. The test results suggested that commercial aviation in the post-war era could embrace jet propulsion without being limited to the modest speeds of existing designs. Aircraft capable of flying at 500 or even 600 miles per hour, cutting transatlantic flight times in half and making global air travel practical for the first time, suddenly seemed achievable rather than fanciful. The economic and strategic consequences of such a transformation were staggering, and governments and aircraft manufacturers in Britain, the United States, and Canada immediately began planning for a post-war aviation industry that would be built around high-speed jet aircraft. The Canadian facility, born from an accidental miscalculation and initially dismissed by foreign intelligence services as irrelevant, had become the crucible in which the future of aviation was being forged. Mackenzie and his team, working long hours in a building that resembled an industrial warehouse more than a sophisticated research laboratory, were generating knowledge that would influence aircraft design for generations. The irony was not lost on them. The same Allied nations that had treated Canadian scientific contributions with condescension at the start of the war were now queuing up for access to a facility that existed only because of a mathematical error and the determination of engineers who refused to accept that what they had built by mistake was useless. As the war in Europe concluded in May 1945 and attention shifted to the Pacific Theater and post-war reconstruction, the strategic value of the Canadian facility became even more pronounced. Allied technical intelligence teams, sweeping through defeated Germany, discovered the full extent of Nazi aeronautical research, including wind tunnel facilities and test data that revealed how far German jet development had progressed. The German research, conducted at well-funded institutions like the Aerodynamic Research Center at Göttingen, had produced theoretical insights that were in some respects more advanced than Allied understanding. But the Germans had lacked the experimental facilities needed to validate their theories at genuine transonic speeds, forcing them to rely on extrapolations and approximations that introduced significant uncertainties into their designs. The Canadian facility, with its accidental ability to generate the conditions that German engineers had sought but failed to achieve, had given the Allies an unexpected advantage in translating theory into practical aircraft designs. Captured German engineers, interviewed by Allied technical teams, expressed surprise and professional respect when they learned about the Canadian installation and its capabilities, acknowledging that they had underestimated Allied technical sophistication and had paid a price for that underestimation. The post-war period saw the Canadian facility transition from a wartime expedient to a permanent research institution that would influence global aviation development for decades. The accidental nature of its creation became a source of somewhat embarrassed pride, a story that captured something essential about the Canadian national character and its approach to technological challenge. The facility was officially renamed the Institute for Aerospace Research, expanded with additional test sections and instrumentation systems that built upon the principles discovered during the original construction. Mackenzie, who had feared that his mathematical error would end his career, instead found himself celebrated as a visionary engineer whose willingness to proceed despite uncertainty had produced breakthrough innovation. He was modest about the acclaim, always emphasizing that the facility's success was the result of teamwork and fortunate accident rather than individual genius. But his story resonated beyond the narrow world of aeronautical engineering, becoming part of a larger narrative about Canadian contributions to the war effort and to post-war technological development. The underestimation of Canadian capabilities that had characterized Axis intelligence assessments during the war reflected broader patterns of prejudice and miscalculation that had strategic consequences. German and Japanese military planners had consistently dismissed the industrial and scientific capacity of the British Commonwealth nations, viewing them as colonial appendages that lacked the sophistication to make independent contributions to modern warfare. This assessment was reinforced by cultural biases and by the very real fact that countries like Canada and Australia had smaller populations and less developed industrial bases than the major powers. But this analysis failed to account for the advantages that came with being underestimated, for the freedom to pursue unconventional approaches without the bureaucratic constraints that hampered larger research programs, and for the particular combination of practical ingenuity and theoretical sophistication that characterized Commonwealth engineers and scientists. The Canadian Wind Tunnel Facility was a perfect example of these dynamics at work, an installation that existed only because a mathematical error had been made and covered up, that had been built to an accidental design that violated conventional wisdom, and that had succeeded precisely because it was not constrained by the assumptions that limited more traditional programs. The technical legacy of the facility extended into every aspect of post-war aviation development. The swept-wing designs that became standard for jet aircraft, the understanding of transonic aerodynamics that enabled the development of supersonic flight, the testing methodologies that allowed engineers to predict aircraft behavior at speeds that could not be achieved in flight tests, all drew on data and insights that originated in the Canadian installation. American and British research programs, once they had absorbed the lessons from the Canadian work, built their own advanced facilities that incorporated and extended the principles that Mackenzie's error had accidentally discovered. But the Canadian facility remained at the forefront of aerodynamic research for more than 2 decades, continuing to generate important data and to train generations of engineers who would carry its influence throughout the global aviation industry. The facility's contribution to commercial aviation was particularly significant, as the economic viability of long-distance jet travel depended on aerodynamic efficiencies that could only be achieved through detailed understanding of high-speed flight characteristics. The human dimension of the story, the experiences of the engineers and technicians who worked in the facility during and after the war, provides insight into the broader experience of Canadian participation in the global conflict. These were individuals who had chosen or been assigned to contribute to the war effort through scientific research rather than direct combat, who worked in relative obscurity while their counterparts in uniform received public recognition and thanks. They dealt with the frustrations of inadequate resources, skeptical superiors, and the constant pressure to produce results that justified the investment in their work. They experienced the satisfaction of solving difficult problems and the excitement of discovering new knowledge, tempered by awareness that their work was ultimately directed toward the purpose of making warfare more efficient and deadly. The post-war period brought a complex mixture of emotions, as the scientific advances that had been driven by military necessity found peaceful applications but also enabled new generations of weapons systems. Mackenzie himself struggled with this duality, proud of what his team had accomplished but troubled by the realization that aerodynamic knowledge could be used to build nuclear bombers as easily as passenger aircraft, that the pursuit of scientific understanding could not be separated from the uses to which that understanding would be put. The final decades of Mackenzie's life, which extended into the 1,980 seconds, allowed him to witness the full flowering of the jet age that his accidental facility had helped to create. He saw commercial jetliners transform global travel, making it possible for ordinary people to cross oceans in hours rather than days, connecting cultures and economies in ways that would have seemed fantastical in the 1,940 seconds. He watched as military aviation progressed to supersonic fighters and bombers, aircraft capable of speeds and altitudes that would have been considered impossible when he first began working on the wind tunnel project. He followed the space program with particular interest, aware that the aerodynamic principles validated in his facility had applications beyond the atmosphere that the understanding of high-speed flight was essential to designing vehicles that could re-enter the atmosphere without burning up or breaking apart. In lectures and interviews conducted late in his career, he reflected on the contingent nature of technological progress, on how many important advances emerged, not from systematic planning, but from mistakes, accidents, and the willingness of engineers to pursue ideas that conventional wisdom deemed impractical or impossible. The story of the Canadian wind tunnel became a case study in the history of technology, examined by scholars interested in understanding how innovation actually occurs, as opposed to how it is portrayed in official histories and corporate narratives. The facility's accidental origins challenged simplistic models of technological development that emphasized rational planning and systematic research programs. It demonstrated the importance of individual initiative and institutional cultures that tolerated experimentation and accepted the possibility of failure. It showed how geopolitical factors and wartime urgency could accelerate innovation by creating conditions where unconventional approaches were given opportunities they would never receive in peacetime. And it illustrated the role of underestimation and dismissiveness in creating strategic opportunities, as the Axis powers' contempt for Commonwealth technical capabilities led them to ignore developments that would have worried them had they occurred in Britain or the United States. These lessons extended beyond aeronautical engineering to broader questions about how societies organize and support scientific research, about the balance between centralized planning and distributed initiative, and about the unpredictable pathways through which knowledge advances. The transformation of Canada's national identity during and after the Second World War was influenced by stories like that of the wind tunnel facility, narratives that depicted Canada as a nation capable of making distinctive contributions to global challenges, rather than simply following the lead of larger powers. The war had accelerated Canadian industrialization and had created scientific institutions that would persist into the post-war era, establishing Canada as a middle power with specific areas of technical expertise and capability. The aerospace industry that developed in Canada after the war, producing aircraft like the Avro Aero supersonic interceptor and contributing to international programs like the Space Shuttle, drew on the knowledge base and institutional experience that had been established during the war years. The wind tunnel facility, expanded and modernized but still operating on the same site where it had been accidentally constructed, remained a symbol of Canadian technical achievement and a reminder that small nations could make contributions disproportionate to their size when circumstances and determination aligned. Mackenzie died in 1987, having lived long enough to see the Berlin Wall still standing but showing cracks that presaged its imminent collapse, marking the end of the Cold War that had shaped the post-war decades. His obituaries, published in Canadian newspapers and international engineering journals, recounted his career and his central role in developing the high-speed wind tunnel that had advanced aeronautical science at a critical moment. Some accounts mentioned the mathematical error that had led to the facility's accidental design, though these retellings tended to soften the story, portraying it as a fortunate mistake rather than acknowledging the anxiety and potential professional disaster that Mackenzie had faced when he discovered what had happened. The engineers who had worked with him, many of whom attended his funeral and shared memories at the reception afterward, remembered him as a demanding but fair leader who had created a culture where problems were solved through experimentation and collaboration, rather than rigid adherence to hierarchy and procedure. They spoke of long nights working to prepare for critical tests, of the excitement when data revealed unexpected phenomena, of the satisfaction that came from knowing their work mattered and was influencing the development of technologies that would shape the future. The legacy of the accidentally brilliant wind tunnel extended into the 21st century, as aerospace engineers continued to grapple with challenges that required sophisticated understanding of high-speed aerodynamics. The specific facility that Mackenzie built eventually became obsolete, replaced by computational methods and more advanced experimental techniques that could simulate conditions beyond what any physical wind tunnel could achieve. But the principles discovered there, the methodologies developed through years of careful experimentation, and the culture of innovation that had characterized the project remained influential. The story itself became a part of engineering education, used to illustrate lessons about the nature of innovation, the importance of pursuing unexpected results rather than dismissing them as errors, and the strategic consequences of underestimating adversaries or dismissing contributions from unexpected sources. In an era when technological competition between nations was once again intensifying, and when breakthroughs often emerged from laboratories and research centers far from traditional centers of power, the tale of how one miscalculation by a Canadian engineer created a facility that changed aviation history remained relevant and instructive. It reminded a new generation of researchers and engineers that progress rarely follows the smooth trajectories depicted in textbooks, that some of the most important advances emerge from mistakes and accidents, and that determination and willingness to see projects through, despite uncertainty and skepticism, can produce results that transform entire fields of human endeavor.